Okay, so taking a look at these again, you had your hand raised for the kinetic energy. What did you say?
Well, since we decided that the velocity was 0, the kinetic energy would have to be 0 because it's half mv squared.
Does that make sense? Yeah, I would agree with that. Let's make sure that we all agree first that the velocity is 0. Is that okay to say that the velocity is 0 right at that turnaround point?
Yes.
Yeah, okay. So we agree with the velocity for sure. And the kinetic energy. What about the other ones? Do we agree with those? Do you have, Jonathan, you take issue with something?
I take issue to acceleration.
Acceleration.
No,
What do you want it to be?
I want acceleration to be minimum.
Why do you say minimum?
Since acceleration is a vector,
Okay.
right, and your block stretched out to the farthest, so it can be outwards, the acceleration will be pulling it back towards equilibrium. Since we have that little coordinate thing on top, which states that its current position is positive, it would be going negative. A greatest acceleration in the negative direction would be the minimum value for it.
What do you guys think? Does that make sense? Yeah. So it depends. It's one of those things that I was talking to, I didn't remember who, somebody, about what does it mean? Like, are we talking about direction, or does direction matter? It does, because it's a vector. So I'd probably change that one to minimum as well. I'm just going to change that. Anything else? So are we okay with that one? There's a lot of thinking that is required in this whole process. Jordan, you've got kind of had your hand up.
Yeah. We were thinking about, and we said that potential energy of the spring was at a maximum because energy it's not a vector, so it doesn't have, like, the direction of it doesn't matter. So we said that because the spring is all the way out at a maximum.
What do you guys think? Does that make sense? Do you
Yeah,
agree with that?
I agree with that.
Go ahead.
Going along with it, like the half kx squared, no matter what x is, it's squared. So like even if it's like positive or negative, it's going to be a maximum.
Ooh. Does that make sense? I always love it when I ask if something makes sense and the person that just said it says, yeah, it makes sense. Like, well, I hope it makes sense to you, because if it doesn't, there's a problem. Okay, so let's change that one. Are we okay here? So you want to change that to maximum as well? Go.
We think that if direction does matter, then the force should be minimum.
Why?
Because if acceleration is going to be a negative, then the force also has to be negative because it's pulling in a negative direction.
What do you guys think? Does that make sense?
Oh, yeah.
I agree. All right. How do we feel about the displacement? We haven't talked about that one yet. Is that one okay?
Yeah.
Okay, cool. Now, my guess is, because I don't even remember who did this, but I'm guessing that there were some other people that are like, oh yeah, I'm going to give you just a minute here with your table mates to talk about it, and if you need to adjust anything, now that we've learned from that experience, we don't need to go through the same hashing out every time. I'm going to give you a couple minutes to go through and fix anything on your chart. If you were the person that wrote something up here, if you would also come up and change it up here so that we can check it based on the right answers, that what you think is actually right now, could you do that? Go. Okay, so let's take a look at B. What do you think? Either put a thumbs up or raise your hand and tell me if you disagree with something. So everybody should have a hand in the air for something, either a thumb or your hand. One of my daughter's favorite books is Hand, Fingers, Thumb. Yes, you know this book? You don't know Hand, Fingers, Thumb?
No. You should read it.
These
I could recite it to you right now. You don't know? Seriously?
No.
I'll bring it in someday. Wow, it's like a classic. It's such a good book about monkeys drumming and monkeys humming. Wow, this is like, I must have skipped a generation because I grew up on it. All right. We okay with this one?
Yes.
The displacement is 0. The acceleration is 0. The force is 0. The spring potential energy is 0. Yeah. The velocity a minimum because it's going which way?
Towards the negative.
The negative direction. And the kinetic energy is at a maximum because it's got to be positive, right?
Yes.
Sweet. All right, this one down here. So we've got a minimum for the displacement. We okay? The velocity is 0. The acceleration is at a maximum because it's going in the positive direction, which is the same direction as the force, right? These guys are always going to match. Have you noticed this? There are some patterns that we're seeing in this, I hope. You're looking at this carefully. The spring potential energy is a maximum because it's got to be a positive number. And
Oh, that should be 0.
Yeah, that should be
this
0.
one should be a
0.
0. Let's change that.
0 technically is the minimum, I guess.
I suppose. Point taken. Point taken.
We didn't.
But
Well, I had 0 written down, but like yeah.
yes,
Yeah.
yes.
It's a semantic
But
difference.
if 0 is one of the options, that would be a better choice.
Yeah.
Yes. Good call. All right. Are we okay with the rest of this one? Yes, though? How about this one here?
0 maximum.
No displacement, no acceleration, no velocity, no spring potential energy. The velocity is now at a maximum because it's going in the positive direction. Kinetic energy is at a maximum because it's a lot of velocity. And then this very last one, hey, this should be the same as the top one, right?
Yeah.
Is it the same as the top one? Let's look.
Yes.
Maximum 0, minimum, minimum, maximum 0. Okay. What do you observe? Take a look at your chart now that it's filled in and it's all happy and good. Do you notice anything interesting? Any, what? Raise your hand and tell me something interesting that you see on the chart. Go, Justin. What you got?
The velocity and kinetic energy match up as long as the masses are the same. But they don't. Do they not?
Do they? Don't they? What do you guys think?
I was wondering
I
if they don't.
think I can change that bit to make it correct.
Okay, you can adjust it a little bit.
Yes,
Speak.
just a little bit. Kinetic energy is going to be the absolute value. It's going to be a max whenever velocity is at an extreme.
Does that make sense? Yeah. Yeah. Let's change
or
that.
The absolute value, or the absolute value of velocity.
So, the absolute value of velocity and the kinetic energy match up. Is that okay? What else do you notice? What other interesting pieces do you see here? You just shared something with me. I want to share the fun because there are lots of smart people in here that can tell me things that you observe. Mira, what's one thing you observed from that chart? Something else that you find interesting.
Well, other than the acceleration and the force being the same.
The acceleration and the force match.
Yeah.
Okay? What else? What else? What else? Go, Ellie.
Absolute value of distance and potential.
The absolute value of the distance and the, you said potential energy? Awesome. Anything else? I think those are the big ones. There are a couple others that maybe aren't matches, but other observations that we can make. What other observations can you make? Maybe that aren't matches, but like the opposite of a match. What do you see?
Like the energies like oscillate, like one's always max, one's always 0, and it goes back and forth.
Yeah, yeah. So the energies, say that again.
Oh, they oscillate, like one's always max, and then the other one's always 0, and then it goes back and forth.
One is at a max, the other is 0, and they go back and forth. They oscillate, right?
And then
Like that. That's the same. Do you see what I'm saying? In the middle there, like if we were looking at the block like right here, what would you know about its energy?
the energies would be equal.
There would be a place,
There
but
would be a
always
place.
like from here to here they're
No,
equal,
there's a place in between where the two are equal.
right? It's transitioning from one kind to another. It's the same as the conservation of energy stuff that we played with last time, like right before break.
Also, can't we tell that displacement and velocity are going to oscillate as well? Because because of the link up we made earlier.
Yep. Yep. So energies oscillate, and the displacement and velocity. Yep.
Maybe they're absolute values, but I think it could still work for them.
Well, one is the max, we could say, or min. Does that make sense?
Yeah.
Yeah. Anything else you see? There's lots of stuff to see from this chart. There's lots of things to see. Hold on, I just want to make sure everybody else gets to play too. Will, what else do you see? There's other stuff.
The absolute value of the force and the kinetic energy are always like
Opposites. I don't know how it is. So like whenever a force is a minimum or maximum, the kinetic energy is 0, and however, yeah.
Okay. So force, the absolute value of force, and kinetic energy oscillate? Absolutely. Absolutely. Yeah. Anything else? Cora, what else do you see? Do you see anything else that's interesting? Fascinating?
The thing I noticed is that the force and the acceleration were the same, but
Uh-huh.
we already did.
We already said that.
So like, I don't know.
What about the force and the displacement? What do you notice about the force and the displacement? What's that?
They're opposite.
Like they're
reciprocal.
inverses of
Yeah.
each other? So when they're 0, they're 0. But when they're not 0, they're always in the opposite directions, right? So that's another kind of interesting thing. You can go on and on and on. We could do this all day, but we're not going to. But let's write that one down because that was kind of cool. So Justin, what did you say?
They're inverses.
The force and, was it the force and the distance, displacement?
Yes.
Okay. So there's a lot of pieces that you can tell with that. Before I want to take that idea in just a minute, but before we do that, you may have noticed that there was one extra row in there. And it wasn't just that I forgot to delete it. Sometimes that happens, but not in this case. I was actually planning on something there. In that row, I want you to label the first column value at the maximum, because they all have maxima somewhere, right? In terms of, oops. K, M, and A, the amplitude. I want you to use all the knowledge, all the cool stuff that you know. I would encourage you to think about Hooke's law. I would encourage you to think about conservation of energy and see if you, and you can work with your group. You don't need to do this by yourself first. You should be able to come up with an expression for each of these things that only have these 3 variables and, you know, maybe some halves and things in there or square roots and things. That's okay. Okay? I'm going to give you a moment to try that out. Think that through. It may take some work on a separate piece of paper to kind of process through that, but I want to see if you can get there. Give it a shot. So let's take a look here. Let's kind of go through one at a time. I want to make sure I feel like everybody's almost there, if not totally. So let's just go through these. Seth,
Yes, it is.
can you tell me the maximum displacement?
You just had A equaling E.
Yeah. Do you believe that, or did you just trust somebody that that was right? You believe it? Can you explain to me why that's the maximum displacement?
Because acceleration, amplitude is basically the same displacement as, well, yeah, it's basically, amplitude is displacement.
Yeah, it's the maximum displacement, right? By definition, so you're exactly right. That's perfect. Okay, so just double checking. Is everybody okay with this one? Yeah? Second easiest one was which? I don't know. What was the next easiest one? Which one?
Force of spring.
Force of the spring. So Allison, what did you guys say for the force of the spring?
K times amplitude.
Was that this one here? K times A, you said? Do you guys agree with that?
Does it need the negative sign?
It uses
or just the-
negative.
Well, it's just the magnitude.
Okay, yeah. No.
So it does yeah. Remember that negative sign is really just telling us direction. So it doesn't really need a negative sign since we're just talking about the magnitude. Is everybody okay with that one? What's the next easiest one to do? Who's got that? Who wants to tell me that one? Next easiest one. Go, David.
Probably acceleration.
Acceleration. What is it and why? How?
So it'd be Ka divided by M.
Ka divided by m. Does that make sense to everybody? Because the net force is Ka, which equals ma, little a, acceleration a. So we're just divide by m. We get that one. All right, 3 down, 3 to go. What's the next easiest one? Keep it as easy as possible. V, what you got?
The spring potential energy.
Spring potential energy. And what did you say for the maximum for spring potential energy?
We had 1/2 Ka squared.
Do you guys agree with that? Perfect. Because K isn't going to change, right? The maximum X is A, so it's got it there. There you go. Okay. Next easiest one. What was next? Jason, what did you guys figure out next?
We said that the kinetic energy was also 1/2 Ka squared.
Okay, and why do you say that? So when it's 0 for potential, it's maximum for kinetic. That's perfect. And here it's 0 for... Yeah, does that make sense? So those have to be the same. It seems a little bit funny to write that as the maximum kinetic energy, but that's all the energy available, so it's got to be now in kinetic, right? All right, and the last one. Anybody get an expression for that yet? What'd you say, Al? Or Dave? I don't know who hasn't talked most recently or something. Go, Allison.
Okay. Square root of Ka squared over m.
Ka squared over m. Is there anybody that would like me to go through that? Yes, let's go through it. Okay, I just want to make sure that it makes sense to everybody because magic is going to happen in the next 10 minutes and I want to make sure that you see the coolness that happens. So, the process there is conservation of energy, right? At the extreme, at one extreme, you've got spring potential energy plus kinetic energy. And in the middle, you have spring potential energy plus kinetic energy. But here you've got no kinetic, and here you've got no spring potential. Is that okay? So you've got 1/2 Ka squared is equal to 1/2 mv squared. Now what? I got it set up. Help me out. Go, David.
You just get v by itself by multiplying by 2 and dividing by mass.
Okay, so you've got the square root of Ka squared over m. I'm going to do one more step just because it's going to be convenient later. If you have a square root of a squared, what's that? A. So I'm just going to pull that a out, but it's the exact same thing. So I'm just going to say this is a times the square root of K over m. Is that okay? Yeah? Issues or questions there? Now, let's take a look at the cool thing that happens here. I want you to look back. So we're going to focus less on those maximums. Those are cool, and we're going to figure out why and how and all of that in a minute. But I want you to take a look at these values, like the displacement ones. Do you notice that it goes to a maximum and then a 0 and then a minimum and then a 0 and then a maximum? And if I was going to plot that, whoa, it's like got a mind of its own today. Okay, I'm sorry. I feel like I have to apologize to my computer. That's ridiculous. If we look at this displacement over time, and I have things, so like I have A, and then B, and then C, and then D, and then E. Are you guys with me? Do you see what I'm kind of doing, what I'm saying here? At A, the displacement is at a maximum. Whoa, hello. don't know why you got such a crazy attitude. And B, it's at 0, and C, it's at a minimum, and D, it's at 0, and E, it's at a maximum. Any predictions about what that would look like? Because I don't have anything in between, right? So I don't know if it's straight lines or what. Anybody have any predictions about what that might look like? What do you want it to look like, Cora? You want it to look like a wave, right? Like if we were going to talk a little math terms, you would say that it looks like a
Cosine.
sine or cosine curve. Does that make sense? So something like that. What about the velocity? Take a look at the velocity. What does it do? What does the velocity one do? Yeah! Woo! She's so excited! It's at 0, and then it's at a minimum. Is that right? And then it's at 0, and then it's at a maximum.
Oh, because it's the.
And then it's at 0. It's a beautiful thing. You're so excited. So for those of you that are not calculus-y kids, they're getting really excited because they've done this in calculus and didn't realize why, but now they see that it's a beautiful, beautiful thing. If you don't know calculus, it's okay. You don't have to know calculus. I just want to show you that it's pretty. Okay?
It's very pretty.
It is pretty. And then you can do the acceleration, and the acceleration is at a maximum and then 0 and then a minimum, and then 0 and then a maximum and then 0 and then a minimum. So we could do that one too. And so that one would look like, well, it starts here and then here, right? So it's going to, are you with me here? Is this making sense? So we got all these funny little curves.
Wait, how did that just. It's not the same.
Did I mess it up?
It's a negative plus sign?
Mm-hmm. Yeah. When you take the, yeah, we'll get there. Hold on, just hold on. Yeah. It's beautiful. Okay, so I want to show you something because it doesn't seem necessarily intuitive to me that it's not going to be just a straight line, especially if I'm not a calculus kid. So what I did was to take video of my object oscillating. And I would like you to pay particular attention to this because you will be doing a lab very similar to this next week. So you may want to, I don't know, pay attention, okay? So I took a video of a mass on a spring, and it's not a perfect video, okay? It was kind of a last-minute video, but I just want you to take a look at it. We can watch this. Oh, and it's going to be really bumpy, but you get the idea. I don't know why it's being so goofy. Anyway, you can see that it happens. I'll show you. Then I put dots, right? So I picked a spot, and I put dots. My camera was moving a little bit. I don't know, there was an earthquake. No, not really, but I was probably just like not really paying attention. And so that's why there's like this displacement in the y or in the x direction. But I've got these dots in the y direction. Let's see if I can watch this video. Maybe it'll be better. I don't know why it was being so cranky. Oh, now it's like really going to be mad at me. I'm really sorry, silly video. Let me try one more time. And if it doesn't want to go, then whatever. Okay, let me back it up just a little bit now. So you can see really it does oscillate, I promise. Let's try it one more time. There we go. Why? I don't know why my computer's being so goofy, but you get the idea. So the point of this is that then I looked at the graph. That's pretty nice, isn't it? That's pretty lovely, I think. I mean, like, that looks like a sine curve to me, right? And not even does it kind of look like kind of plus or minus, but just kind of a friendly reminder to you that you can get these things approximated, right? So you hit the little button up here that says find a curve, and hopefully my computer won't die. Come on, team. There we go. And you can choose things like you could say, oh, it looks like a line, and it would approximate it to a line as best it could, which it wouldn't do well. Or you can use the sine one, and I'm going to say try fit. And oh my gosh, it looks pretty darn close. And oh my gosh, it gives me a really nice expression here for, maybe, oh, cancel, for that curve. So there you go. Does that kind of make sense? Okay? Now, if you flip your yellow sheet over, you'll see a screenshot of this exact thing with not only the displacement curve, but I also allowed it to calculate my velocity curve. And you'll notice that that is a really nice right, of that first one.
Inverse cosine.
Okay?
Opposite
Now,
cosine.
when you look at the expressions, those equations right there, they actually mean things. And as Physics 1 students, you need to know a bit about what they mean. Okay? So I want to walk you through some of the pieces of that equation. Not all of it really matters, but some of it does. So for some of you, this is a nice review, and for some of you, this is like brand new weird stuff. Either way, it's all good. I just want to kind of share with you a couple of pieces that go with this. So I'm going to get myself a new page. New page. You'll notice that we've got, I'm looking at the displacement equation, and it says y equals a sine bt plus c plus d. Do y'all see that? The sine and cosine graphs that you play with in math, in pre-calc, in calc, and that sort of thing, usually are going to look more like y equals maybe like a sine bt. Does that look a little bit more familiar maybe?
Sometimes BT.
Okay. I'm going to not worry about the C and the D. Those values are just phase shifts. They're just like when I decided to start taking the data. So you can ignore those two pieces, okay? But this one and this one mean things. And I want you to understand what they mean, okay? I want to think about this carefully. Whoa. We were just talking about minimums and maximum, right? What is the minimum value of sine?
-1.
-1. What's the maximum value of sine?
1.
1, right? So this is really just adjusting from -1 to 1. This whole thing here is just adjusting from -1 to 1. And if it's 1, that's going to give you the maximum value of this function. Are you with me there? So this A right here is the maximum value of the displacement graph. Okay? Now, this, because I didn't adjust this to make it at 0 and all of that, but if we look at the displacement graph for a simple harmonic oscillator, the displacement graph, it is A, okay, which is the amplitude of the graph times, now we noticed maybe on this last one, on the chart that we did, that it's the way that we had it set up, it starts at it's cosine, okay? Sine and cosine are really just phase shifted of each other. By that I mean they just like moved over, right? Because they're all just up and down and up and down. So when we define displacement, we usually write it as cosine. So don't freak out about that sine cosine thing. And then there's something in here that we're going to talk about in just a second, times time. Okay. But this is the amplitude of the oscillation. Take a look at your graph. Take a look at the yellow graph and look at the value for A. It's kind of hard to read. It's kind of little. But what does it say? What does the value say for A? Everybody see it? 0.03650. So that's a displacement measured in meters. So what is the amplitude of the oscillation in the video that wasn't very nicely seen? What was the amplitude? In centimeters. 3.5 centimeters. Yeah. So right from this, we can tell exactly what the amplitude was. Does that make sense? Okay. This piece over here, this thing is called omega. And we're going to get to know omega really well next semester. But the things that I need to tell you about omega right now are that a lot of people think it looks like a W, but it is not. It is omega. Say it with me.
Omega.
Omega. It's the last letter of the Greek alphabet. It's way over at the end there, okay? And omega describes, it's related to the frequency. Remember we talked about frequency last time we were together? The frequency is how often something happens. We'll talk about why it's true later, but the thing that I want you to know right now is that the frequency that we know and love, times 2 pi gives you omega. Okay? Put a box around that. We'll start there on Friday. I hope you guys have a fantastic Wednesday.